Welcome back to Linear Circuits. I'm Dr. Harris. The topic of this lesson is power. And by the end of this lesson, you should be able to define power, as well as understand how power relates to voltage and current. Power is extremely important when you're designing electronic circuits and devices because of power dissipation, power requirements. So let's look at power and see what it means. This lesson builds upon two things. First is the concept of electric current, which is the quantity of charge that passes through a given area in a specified time. And remember that current is dq dt. This lesson also builds upon voltage, which is the energy gained or lost by a coulomb of charge. And remember that voltage can be written as dw dq, or change in energy per coulomb of charge. So building upon those two concepts, what exactly is power? Well, remember that a charged particle Q flows over time to produce a current I, dq dt. And a voltage is produced by the energy that's either lost or gained by that moving charge, or dw dq. The power is the rate at which that charge's energy, W, changes over time. So power is the rate of a charge's energy changing over time, or dw dt. So if you look at our definitions for current, voltage, and power, you see that power can also be expressed as a product of the current and the voltage. If you use the chain rule, you see that dw dt is the same as dw dq times dq dt, or V times I. So power is the product of voltage and current. We're going to use the variable P for power and the unit watts, which has an uppercase W, not to be confused with the lowercase w that we use for energy. So given that definition, that power is the product of voltage and current, let's take a short quiz and calculate the power for a known voltage and a known current. Pause the video, solve these problems, and then we'll solve them together. So let's take a look at this first circuit. We have 5 amps of current flowing from the plus to the minus and a voltage of 2 volts. We want to calculate P1, and we need to know if power is either generated or consumed. We know that power is the product of the current and the voltage. Now in this case, the current is going downhill from plus to minus. And as a mnemonic device, I always use the sign that I get to first. So a positive 5 amps times 2 volts, or in this case, the power is a positive 10 watts. Now, because power is just flowing downhill, meaning the current is flowing downhill, it's not taking any extra energy for this current to flow from plus to minus. So this power is actually consumed. Positive power is consumed. Now let's consider P2. We know that power is current times voltage. But in this case, we have 4 amps of current going from minus to plus. So it's taking some energy. The current is it's opposing the direction that it really wants to flow. It's flowing uphill. And again, I take the sign that I get to first, which is a minus. So I'll say a minus 4 amps times 3 volts, or the power is a negative 12 watts. And we required some energy to get this current to flow from minus to plus, which means that in this case, power is actually generated. So by our convention, if the current is flowing downhill from plus to minus, and you have a positive voltage, positive current, then we have a positive power is consumed. In the other case, power is flowing from minus to plus, so we end up with a negative power. Remember that negative power is generated. Another interesting fact about power is that the sum of power generated and consumed in a system is 0. Because power is the rate of change of energy, and energy is always conserved, the sum of power generated and consumed in a system is 0. We know that energy is conserved. We're neither creating nor destroying energy. And since power is simply the rate of change in that energy, the sum of power also has to be 0. So take a look at this system. You have an unknown power with 3 other sources that are generating and consuming 3 watts, -7 watts, and 6 watts. What is PX? Yeah, think about it. We have +3 + 6, which is a +9, and a -7, which means that PX must be -2, because -2 watts and -7 watts totals -9 watts, and +3 watts + 6 watts equals +9 watts. So 3 and 6 is 9, 2 and 7 is 9. PX must be a -2. So let's take a moment to use power and find an unknown voltage and current. Pause the video and solve each of these problems on your own, and then start the video again and we'll solve the problem together. So let's consider this problem on this side. We know that the sum of the powers, PX, this unknown power, plus 4 watts plus 8 watts minus 6 watts equals 0. So 4 and 8 is 12, minus 6 is plus 6. That means that PX has to be a minus 6 watts in order for the sum of the power in this system to be 0. Well, we also know that the power is the current times the voltage. We're looking for the voltage Vx, so the voltage is power over current. We know that our power is minus 6 watts, and our current is 3 amps, so our voltage is minus 2 volts. Let's try this next quiz to find Ix. Again, we have some unknown power, plus 2 watts minus 3 watts plus 4 watts equals 0. 2 and -3 is minus 1, plus 4 is a positive 3, so PX has to equal a -3 watts. In this case, we're looking for the current, which is power over the known voltage. So we have a -3 watts divided by 2 volts, or our current is -1.5 amps. So if you understand, or if you know the power in a system, you can use that power to find the current or the voltage, given you know one or the other. The key concepts that we covered in this lesson are, first, that power is the rate at which energy changes over time, or dW/dt. It can also be expressed as the product, which is most often the form of V and I. So most of the time you use power is the product of the voltage and the current. And finally, the sum of power generated and consumed in a closed system is 0. So if you know all of the power generated or consumed of several of the elements in a system, you can use those to find the power of an unknown element. And you can also use that power to find an unknown voltage or an unknown current. Thank you.